Hello, my name is Jeffrey Downing, and I'm here to talk about my final project on grammar detection and correction. This project aims to explore how natural language processing can be used to detect and correct grammatical errors in English text. So, as someone who had some difficulty learning grammar growing up, I was often corrected until eventually I developed the intuition on my own. And so I was motivated to design a model that could provide similar feedback for others at scale. And so AIs learn through exposure large amounts of labeled data in a similar way that we learn. So using natural language processing seemed well suited for this task. So my research question is, how do different NLP architectures perform on grammatical error detection and correction? And what are the limitations that can arise from the model's design as well as the dataset's composition? This project focuses on two key areas. The first is grammar error detection. So I started by building a sentence classification model to determine if a sentence is correct or not. I built a model using recurrent neural networks with long short-term memory cells as well as BiLCM. And then I built another model using the BERT architecture. The second key area is grammar correction. So I built a model that takes an incorrect sentence and turns it into a correct one. And both of my models use a sequence to sequence architecture, which is often used in machine translation. So I used the English grammar error dataset from Kaggle, which contained 150,000 training and 35,000 validation examples. Each entry contained a pair with an incorrect sentence and its corrected version. I then took the 15,000 sentences and split that into a training set and a validation set. And then the 35,000 sentences were set aside to use as a testing set. The strings were converted to lowercase and white space was stripped. Entries with missing values were removed to ensure that every incorrect sentence had a correct counterpart. And a few of the sentences in the test set leaked into the training set. So to avoid data leakage, I removed those 859 sentences. For my classification models, I started by building two models using recurrent neural networks. I thought about potentially using a TF-IDF, but given that grammar is dependent on word order, that did not seem appropriate for the task. So the words were tokenized with a vocabulary of 5,000 and padded to a maximum length of 30. Both models used an embedding layer with 100 dimensions. And the first model's architecture, which you can see on the right, uses 3 LSTM layers. And this model was trained for 15 epochs. So the model starts by taking a sentence, it tokenizes it into tokens, it's run into an embedding, so that's increased its dimension to 100, and then it's run through 3 LSTM layers with 64, 64, and 32 nodes each, and then that's run into a dense layer, and after that we get a prediction where the model predicts whether or not the sentence is correct. The second model's architecture is very similar, but the key difference is that it uses a bidirectional LSTM instead, and there's only 2 layers. As for results, the first model achieved an accuracy of 78.1. The second model was very close with a 77.3. The models performed very similarly. The models performed well on simple errors like missing or incorrect articles. The model did have a little bit of trouble with larger sentences, but it was able to categorize a fair amount of them. However, in the test data set, I noticed that a couple of sentences were mislabeled. For example, the one on the bottom right, the sentence, "I don't like practice," is technically grammatically correct, and the model predicted it as being such. And then on the bottom left, the sentence was really long. There was one mistake in there, and the model was just not able to detect it. For my third model, I implemented the BERT architecture to improve performance. So BERT stands for a bidirectional encoder representations from transformers, which can capture contextual information from both sides of the sentence instead of going through the sentence sequentially. And so this model was trained for 4 epochs. And the test accuracy of the model was 80.6%. So this ended up performing the best out of all of my models. And the strong performance suggests that transformer models can offer further improvement in grammar detection. Moving on to my correction models, they both use a sequence-to-sequence architecture, and these are often used in machine translation. So for my fourth model, going through the architecture here, we start with the incorrect sentence that gets run into a text vectorization layer, which tokenizes all the sentences. It's run into a 128 dimensional embedding, and then afterwards that's run into the encoder, which features 512 long short-term memory cells. And we don't actually take the output of the encoder itself, but rather we take the short and long-term memory states from each of the nodes. And on the decoder side, we have our correct sentence. We add a start of sentence sequence token to the front of it that is run into the text vectorization layer where it's tokenized, and then run into a 128 dimensional embedding. And then that, along with the short and long-term memory cells, get passed into the decoder, which is also features 512 LSTM nodes. The result of that is fed into a dense layer, and then we get our predicted sentence, and that comes with a end of sequence token. So to generate correct sentences, the seek-to-seek model must be run repeatedly in order to predict each new word in the predicted sentence. And so because of this, calculating accuracy itself may not be as useful. So instead, I used the BLUE score, and this is a metric that compares n-grams between the model's output and the reference sentence. And it assigns a score based on how similar the sentences are. The model performed well with short sentences, but it really struggled to reproduce longer ones. So you can see on the right, shorter sentence, the model was completely able to create the correct sentence. But for the larger sentence, it kind of veered off into a completely different direction, changing a lot of words in there. So because of this, I decided to restrict my evaluation to sentences with 12 words or less just to see how well the model performs in this subset. And it turns out the model was actually able to make very good and accurate corrections. So I decided to evaluate on a sample of 1,000 short sentences, and I got an overall BLUE score of 0.7151. And so it appears to indicate strong performance. For my final model, I decided to add an attention layer just to see how well that could possibly improve results. Adding the attention layer can allow the encoder's outputs to be used when making predictions. And so the key difference in this model's architecture is that the encoder's output is also saved, and that combined with the decoder's output is sent to an attention layer, and then that uses both the encoder and decoder's results to make predictions. That's passed into the dense layer, and then we get our predicted sentence. And this model performed much better on the reduced test set. The model achieved an overall BLUE score of 0.7862, and it appears that some of the loss was because of out of vocabulary words, as well as potentially mislabeled entries. So we can see in the first sentence on the top left, the correct sentence says at the weekend, but the model said on the weekend, and I agree with the model. I think that is a better correction. For the sentence on the top right, that lost some score because breads was not in the vocabulary. On the bottom right, some score was lost because it said got in the plane, which I think both got in the plane and got on the plane are grammatically correct, so the model just picked one of them. So one key issue I encountered was that the model was only able to correct one kind of sentence. The model performed well at correcting preposition errors. So this is when words like in, at, for, or to are used incorrectly. And these were the most dominant error type in the training set. And so the model did not receive enough exposure to other types of mistakes. So you can see at the bottom of the screen, I'd made my own custom sentences, 2 of them with preposition errors, and the model was able to correct those. But I did try also using subject-verb agreement errors, and the model was unable to correct those at all. So given more time, I would had seeked out additional data sets that cover different kind of mistakes that can help the model learn more unique patterns. Another limitation of these models is their inability to handle words outside of the vocabulary, which could lead to incorrect predictions. So for future improvement, I would like to use something like, say, a named entity recognition to classify words by their role and potentially feed that into the model instead. So we could check if a word is a name, location, a company. We could also check the word's tense, because that's also important in grammar. And then we can also check the word type itself. Is it a noun, a verb, an adjective? And so this could potentially help the model identify or correct mistakes that are outside of its vocabulary. So at the bottom of the screen is just an example of what this could look like. A key limitation of the sequence to sequence models is that they had to reconstruct the entire sentence when only a small portion needed correction. And so this made the task unnecessarily difficult for longer sentences. So for future improvement, I would consider breaking the sentence down into segments. Could run the classifier model on that to detect errors, and then run the corrector model on just that small portion. And so that way, that can alleviate some stress on the correction model. So at the bottom of the screen, I have a long sentence. I split it into different parts. The classifier model detects two areas where there are mistakes, and then we could run the correction model on that and get our fix. So overall, this project demonstrates how NLP methods can be used to identify and correct grammatical errors. For the classification models, recurrent neural networks achieved solid performance on simple sentences, and BERT was able to capture more context, and it overall achieved the highest accuracy. For correction models, sequence-to-sequence models showed promise for grammar correction, and adding attention improved the model's performance substantially. And blue scores indicated good performance on smaller sentences. And so with continued refinement, I think these models have some strong potential for real-world use.